For our last guest today, who will be delivering the talk remotely from Tokyo, is Tennin Yan, CEO of QunaSys Systems. So Tennin graduated from the University of Tokyo from the Department of Mechanical and Information Engineering. And after sort of entering the graduate school in information science here and then studying sort of abroad also at the Technical University of Munich, he sort of got a second management degree and came back and decided to return to Japan to launch a startup known as QunaSys. So QunaSys, the aim of it is really to bring the power of quantum information, quantum computing into the chemistry domain. So in chemistry, there are a lot of complex simulations, and a lot of it is based on, well, quantum mechanics. So it's naturally one of the first places where we think quantum computers can have remarkable applications. And so Tennin has been really sort of, he has started a very promising startup in this area based in Tokyo. And I had the pleasure of actually visiting QunaSys just a couple of months ago. And I thought it'd be great sort of as part of this industry day to share some experiences, not just from the startups here within Singapore, but from the greater international community as well. And Tennin has kindly volunteered to tell us a bit about QunaSys, as well as sort of the potential for quantum computing to chemistry as a whole. So thank you very much, Tennin, for joining us, and the floor is yours.
Yeah, Professor Gu, thank you for your kind introduction. So, hello everyone, I'm Tennin Yan from QunaSys, and I'm a CEO of this company. And kind of today, I would like to introduce what is QunaSys is doing, but also like the kind of want to introduce to everyone in here, like what is the how does the startups work in the whole quantum industry. So kind of I think what we are really different. So we are not universities research facility, but we are doing startups. So what we are doing is not just building technology. We also do engineering to make that algorithms useful and easy to use for end users. And also just like building that software is not enough. So we want to build community, how the end users understand this technology and to expand and kind of start using this technology. So that is kind of what we think is essentials in here. And kind of I would like to introduce about that. Okay. Yeah, unfortunately, I cannot see anyone in the my camera, but yeah. Okay, so kind of a brief introduction of QunaSys. So we are founded in 2018, and currently we have 40 people, and we are currently based in Tokyo, but we will soon open our office in Europe. And currently we have 15 PhDs as employees, and we have several interns. And we are a company founded with Keisuke Fuji. So he's one famous quantum error corrections researcher in Japan. And we also, with him and several quantum algorithms researcher, we founded this company. And as introduced, QunaSys is building algorithms and software for the chemical calculation on quantum computer. So that is a brief picture of what we are doing. So kind of what we believe is like the chemistry will be the first application of the quantum computer. So this is like the Feynman says, if you want to simulate nature, so you better do it quantum mechanically. So we believe like the quantum mechanicals computing devices is good at calculation of chemistry, and especially quantum chemistry. So quantum chemistry is problems that you understand how the electrons behave in the molecules, and that is kind of even with a small number of electrons, it's extremely hard. So it is a small size problem, but extremely hard. So I think there's a good fit of the quantum computer because the number of qubits is not huge. So what we believe is that the chemistry will be the first application, and we are focusing on building chemistry software. And kind of, I think what our strength is like that there's a lot of companies in quantum chemistry, machine learning, optimization, etc. But we are like have strong focus in chemistry. So we do from algorithm development for building the tools and that make easy tools for end users to use it. So I think this is our core competence, and I would like to introduce like what we are doing. So kind of as a startup, so we are not just focusing, of course we are focusing on research, so expand potential of quantum computers, but also like the expand potential users and make ecosystems. So that is kind of what we are doing, and I would like to introduce each of that. Okay, so first is like the expand the potential of what quantum computer can do. So far since we found it, we've published like more than 28 papers in 4 years. And kind of what we are doing is, you might know these algorithms, but you don't have to, if you are not, you don't have to understand this totally. So what we are doing is there's algorithms called variational quantum Eigensolver. So what these do is like tuning the parameter in the quantum circuits, you get the ground state of the molecules. So it gives you the ground state energy of the molecules. So this is the one way that using the near-term quantum computer or NISQ devices and considered to be one useful applications. And if you have tested these algorithms a lot, you might know there's a lot of problems on these algorithms, but we are really on our research side, we are working on how can we overcome the limitation of these algorithms. But kind of one algorithms we are focusing on is this variational quantum Eigensolver. So calculation of ground state in the molecules. So you can understand some chemical reactions precisely, but just that the application is really small. So what we've been doing is expanding based on this algorithm. So what industrial application we can make based on this. So that is kind of what we are working on. So this is the one example. We worked with Mitsubishi Chemical. So they are one of the big chemistry company in Japan. So that is what we are doing is calculation of the excited states of the molecule. So if you want to, for example, design an AMOLED display, so you have to know the excited states, and that the gap between ground state energy and excited states energy is like it will be the color of that AMOLED molecules. So what we're doing is like the calculation of excited states. There's a conventional method called TD-DFT, time-dependent DFT. So that is rather doesn't give you the good result. And we see quantum computer might be more powerful to calculate the excited states. So we've been working on like to make the excited states algorithms and calculate some properties related to excited states. So that is, for example, called like transition amplitude, the couplings, and spin orbit couplings. So kind of what we do is like based on that VQ algorithms and expand to more broad application in industry. So that is one thing we are doing. Another thing, this is also similar, based on variational quantum Eigensolver, expand more application. So what we do is like the calculation of energy derivatives. So if you can get the derivatives of the energy, you can get the force. So I think you might kind of learn that in high school also. So kind of if you can get the force, so you can know what force apply to molecules, and you can do, for example, molecular dynamics simulations. So like this, or like doing reaction root search, or if you can get second energy derivatives, you can do vibration analysis. So that is kind of what we done in here. So doing project with ENEOS, so one of the big energy company in Japan, where we worked in calculation of that frequency mode in the real quantum computer like Qamuy devices through Microsoft platform. So kind of what we've doing is like as explained, like the based on VQE expand to do more industrial relevant application. So that's like the brief highlight of our algorithms development. So now there's a lot of algorithms we developed, but kind of we don't want to just limit and put that is in open source. But so some chemical company can use it, but it will be really tough for the true chemists to use it. So what we're developing is like the cloud software that everyone can easily access our quantum computing algorithms. So yeah, I will go into that. So kind of we have a building software called Qamuy, and so far there's more than 3 million API access on this. And what we do, and they do mainly is like they throw the job and we execute on simulator, but we have some features connecting to real quantum computer, like some devices through AWS and IBM. Yeah. So what is this software Qamuy? So this is a computation chemistry software as a service and using quantum computers or the quantum algorithms. So kind of, the current quantum computer, it doesn't have quantum advantage. So if you want to calculate bigger molecules, so you better use a classical computer. So you cannot, using these tools, unfortunately right now, you cannot find real new chemical reaction, etc. But what we do in here is like more like kind of for educational purpose. So like for the undergrad students to understand how the quantum algorithms work, or for like for industrial users to know state-of-the-art algorithms, and for them to analyze if these algorithms is useful for them. So if these quantum algorithms doesn't work in small molecules, it will never work in real bigger molecules or real noisy devices. So what we have to do is like the testing algorithms on small setups. Yeah. So this is really the simple to use software. So for the chemistry companies, so what they're interested in molecules, so not building quantum algorithms. So what they do is like they prepare some molecules they want to input and just specify some quantum algorithm they want to use and throw to our system, and our system automatically make quantum circuit and gives them back the result. And kind of this kind of make them easy to test and validate quantum algorithms. And so kind of as explained, what our software can do is basically calculation of the molecular properties. So like the understanding the molecules, there are several properties you want to understand depending on what types of the are kind of the molecules it is. So for example, like as I explained, like getting basic ground state energy is important to know, understand the chemical reaction, but also to understand photoreactions related molecules. You want to know excited states of the energy, and also our algorithms gives you the gradient Hessian, the first energy derivative, second energy derivatives, and so on. And kind of what similar to the classical quantum chemistry software, what the end user can do is combining these algorithms to do more industrial relevant study. So like doing reaction path search, molecular dynamics simulation, etc. And user can easily change what algorithms they want to use and see what is the kind of algorithms that will be best suited for them. Yeah, so kind of I won't go deep in here. So this is really kind of some small toy problems of the true chemistry application. So like doing reaction path search, running molecular dynamics, and seeing the photochemical spectrum, etc. So, and also we are able to calculate the band gap of the periodic system. So yeah, so this is the tools we are building, but it's kind of unfortunately what we've we made these tools, but we find out there's not many chemistry end users is able to use this, because we go to present with them, and first of all, they don't understand what is quantum computer. So it will be kind of, and they have interest, but they are kind of bit far from using our tools and doing R&D and understand what quantum computer is and be quantum ready to use quantum computer. So what we're doing is kind of expanding the ecosystem. So building the research community in Japan. So what we've make, so you can search this QPark, and there's a website on that. And what we do in this QPark is like, we've more than like 50 companies in Japan right now, and we want to expand this globally. But currently it's in Japan right now. But there's a lot of chemistry companies and like the Toyota, Panasonic, so like the motor company and the electronic companies is in here. So we gather them, and what we are doing is like the kind of make really start with basic lecture. So what is the quantum computer? Why these are devices can do first principle calculation or the quantum chemistry calculations. And then we work together to find the industrial application of the quantum computer. So kind of that is what we are doing, and we want to show some result that built by these end users. So like the kind of one is use cases of reaction root search. So kind of there's one software package called Global Reaction Route Mapping Software. And so this is one package built in Japan, and kind of a lot of end users use it, but doing reaction route search in this software package is really time consuming, and they have some wish to speed up this, and they see quantum computer might be useful on this. So there's several companies, they gather together and connecting that software to our software Qamuy and kind of tested our algorithms. So, and kind of the result is quite interesting, and this is like the technical detail, so I won't go that detail in here. But like the classical devices, it gives you a route that have here, but something in quantum algorithms, it gives you a new route that couldn't find in the classical devices. And this is like the reason is like there's spin transitions in the middle of these reactions, and quantum computer can naturally describe that. So they thought that this will be kind of one interesting way that kind of to find reaction route that with the spin transition inside. Okay, so other is like the calculation of the, like, for example, periodic systems. So this is really like the more academics demo. So like the more pious transitions. So like if you put the hydrogen's atoms in same coordinate, but the making the hydrogen's molecule is more stable. So there will be like the transitions of the energy. And so that is kind of some demo they make together. So what we believe is like through like we build these algorithms for them to use, and then test it for what will be the useful use cases, and gives us the feedback that will be kind of drives to the real application of the quantum computer. So that is what we are doing. So as a goes back to the this slide. So kind of I think I think we finished like the first phase of building new algorithms and putting the software, and let end users use it, and let end users understand it. And we are currently working on how can we more fundamentally improve in these algorithms. So that is kind of really needed in this quantum computing field, and we are like happy to collaborating with everyone, like the building more breakthrough in quantum computing algorithms. And we are also kind of expanding this cloud software. So also in the real quantum kind of quantum computing users, but also in university or for educational purpose, etc. So yeah, these are like the brief introductions of the QunaSys. And yeah, I will stop here. So we would like to welcome any questions from the floor. Thank you.
Right. Thank you for the excellent talk, Tennin. So we're going to take some questions from the audience. Unfortunately, the camera seems to be facing me rather than the audience, so you don't quite see them. But Trish, so there's about 100 people here.
Wow, great.
So I think you've got the microphone to give the audience. So for this case, we'll have to use the microphone because that's the only one that goes through Zoom. So if you have a question, ask away and we'll bring the microphone to you. Yeah.
Thank you for your very interesting talk. I have a question on the, the motivation for the chemist using the quantum software, because my imagination is very hard for you to engage the community, the chemistry community, to use your software when they haven't seen the advantage. So they just, I think the motivation at this moment might be just get familiar with the system and hope for the future. Is that correct?
Yes, exactly. So for the chemist point of view, so they want to understand the molecules better. And for that purpose, quantum computer doesn't give the speed up compared to the classical devices. But what I think that chemists interested in right now. So, but still the classical devices has limitations. So they are interested in these new devices and want to try out what potentials of these devices can do. And kind of there's kind of, at least in Japan, there's a growing interest in that. So kind of we are working with them to, build find application together and find use cases together. And I think that is something important in this phase. So more user-led innovations. So not just our as a developer build something, but also users consider potential application, and we work on how can we make that applications useful closer using our technology. Yeah, thank you. That's great question.
Thank you. Any further questions? Yep. Over there.
Thank you for. Yeah.
Okay.
Hi. So I'm a current chemist undergraduate and I'm kind of interested in computational chemistry. Can I ask if like you're hiring for interns?
Okay. I think unfortunately currently it's not, but we I think from next April we will open our interns. So yeah, please check our website. And also like we have unfortunately it's in Japanese, but kind of QunaSys textbook, they also have like a lot of chemistry application. And so I think it's kind of good like you learn it there. Yeah. And,
okay, thank you.
And we are always happy to do research discussion. Thank you.
Thank you for the very interesting talk. It seems to me that you're doing some quantum computing equivalent to DFT. I'm wondering, have you considered extending this to condensed matter systems? Because I think that DFT for condensed matter systems has some limitations. So do you think that quantum computing has some advantage to overcome those type of limitations?
So like the periodic systems, or like the condensed matter basics, how to say?
Like for example, materials.
The materials, right? Material science.
Yes.
Yeah. So for example, the QunaSys is building some algorithms to calculation of the band gap of the periodic system, and that is kind of this last demo is also calculation of periodic system, but it's hydrogen's chain, so it's kind of small. And yeah, I understand kind of the material science, that market is more bigger. But unfortunately, like current quantum algorithms need a lot of resources, qubit, to calculate this. So yeah, kind of we are still exploring that, and kind of the how quantum computer can be useful for material science is currently not unknown. That is, I will describe current situation.
Thank you. Thank you.
Thank you.
Yeah, thank you very much for this talk. I had two questions related to your to the communication with these big companies, let's say Sumitomo, Mitsubishi. Are they looking for you, or are you looking for them? And then the second question is, what are the people that you are talking to in these big companies?
Okay. Yeah, please. Are there?
Yeah. It's R&D people or other departments in these big companies.
Yeah, really good questions. So they are looking for us, we are looking for us. I think it's both way. So we want to have users of our software. So we are looking for them, but also they are interested in, so there's kind of big buzz in quantum computing field. So they are interested in what this technology can do and how can they benefit for their companies. And kind of a good thing of this quantum computing field for the chemistry company is like, this is kind of their tools. So kind of their real true goal is like building the chemistry compound, etc. But the quantum computing is just one computational tools. So they are kind of happy to collaborate on here and build algorithms together and test it together. And kind of people we are working on is mainly, as you explained, like the research team. So computational chemistry team that are running a lot of supercomputing simulations, and they are interested in quantum computing, and they come here and learn quantum algorithms together with us. And then they form a team if they have same interest and test these algorithms. Does that answer your questions?
Yeah, thank you.
In that case, I'll continue with a quick question on this end from the students, which is that what sort of skill sets do you look for when you want to hire people in sort of your company, and the sort of, both in sort of scientist level positions or perhaps in more general positions as well?
Yeah, that's a really good question. So kind of on the research and engineering, I think it's slightly different. So kind of as building new algorithms, so we believe like you need like the PhD levels. So kind of what we think in here is really important to you go to a new field and learn some techniques there, and kind of how can we, and think about how can we that some new techniques can apply to quantum computing. So I think that is like really need like the PhD level skills. And kind of like in cloud service, that is more like the software engineering side. But what we think is like still we need like the quantum chemistry expert or the quantum information experts, but kind of we kind of require is more like the software engineering skills on that. So that is like that. And also like in the business side, like we are like running the research community, etc. So that is more kind of doesn't have like really special skill set, but needs like basic understanding of this chemistry field and quantum computing field.
Right, thank you. And do you have any, so do you hire on an international level for remote work? For example, if students were interested in these in Singapore, would they need to go to
Yes.
Japan, or would they be able to take an internship or work remotely?
Yes, they can do totally remotely, but currently Japan border is open, so it's welcome to come if you are like be a full-time. But currently in QunaSys, we totally work remotely. So like from north side of Japan to south side of Japan, and we also have Europe teams in Europe, like 4 people in Europe right now. So kind of, yeah, we are totally working remotely. So it's no problem that you work from Singapore.
Great. Thank you very much.
Yeah, and maybe last one kind of not announcement, but message. So what we think, so if you are studying these variational quantum algorithms, so currently these noisy quantum computers, and you can find there's a lot of problems on this. So like, for example, like there's a lot of updates on these parameters. And if you want to update parameters, you have to get gradient of this. But if you have a lot of qubit, this will, I'll say, disappear gradient. So kind of, but we believe like through like working like the more researchers come into this field, and we together think about how can we overcome this limitation of current quantum computing algorithms. That is really important, and like maybe in the like the next February or March, that we want to launch like more like half-year competitions to build better algorithms. So kind of define some problems and everyone compete to come up with better ideas. So kind of I will I will let you know about that. And so if some students is interested in participate that, yeah, please participate.
That would be great. We'll be sure to forward that.
Yeah.
Excellent. So one last chance to ask a question. Yep.
I have a question on the paper, the scientific paper you publish. Is it on the chemistry or in quantum computing?
Okay. So I think the answer is both. So like the building like basic quantum algorithms, like we published in the quantum computing journals. But if you want to make some demos that kind of use like some algorithms that is not really new, but building some demos using these techniques, combining these techniques and make some chemistry demo, we published in the chemistry journal. So we require like as a hiring, quantum information expert, more computer science expert, and also a quantum chemistry expert. Yeah,
but when you do for the chemistry paper, do you have to reconfirm it with the classical computer?
Yes, kind of. I think everything we do is like really small size. So everything we do, we can get the called full CI, like exact number. So kind of we always compare the result with that. And I think this, like for example, exact is also like the classical, like the exact number.
I see. Thank you.
Thank you.
Right. Thank you very much, everyone. I think it is the time for lunch, and thank you so much, Tennin, for joining us this afternoon. It's a morning. It's a real pleasure to have you here, and hopefully we'll see you in Singapore in person sometime.
Yes, excited to be there. Thank you, everyone.
Great. Thank you very much.
Yeah, feel free to contact me.